Yeah, so we are in question 3. You're told to solve this differential equation, and then the solution you obtain must satisfy this initial condition here. So this is like saying you're solving a differential equation given the initial condition when x equals 0, y equals 1. That is, y of 0 equals 1. So this, together with this, is an initial value problem that I want to solve. And when you solve the two of them, you're expected to obtain a particular solution. So the first thing is we would like to solve the differential equation first. So you're writing the differential equation, we have x dy dx equals y squared minus y. Now the next thing you want to think is, which technique am I going to use to solve this differential equation? A very quick and easy way to do something like this is to first start by thinking of the simplest technique. And then one of the simplest technique is separable method. You try and see if there is a way you can separate all the y's. These are all the y's. These are the y's that we have here. And then the x. Is there a way I could put all the x on one side and then all the y's on one side? Now from what we see here, it's possible. All the y's can come here while all the x will go to the right hand side. Now in doing that, we have the y all over y squared minus y equals, we have the x, then x comes under all over x. Now from here we integrate both sides. Now looking at this side here, this is the same thing as the y divided by, now y is common, into y minus 1 equals the integral of the x all over x. But there's something you observe here. Now it's not easy for us to integrate something like this. So the very quickest thing, or the next thing you can think of, is how then do I resolve this partial fraction here? This is like 1. So how do I resolve 1 all over y into y minus 1? I want to resolve it into partial fraction. So it will be easy for me to find the integration, that is the indefinite integral. Now, the next thing I'm going to teach you is how do you resolve this into partial fractions. So what we have here is 1. So resolving 1 all over y into y minus 1 into partial fraction. Now to resolve this into partial fraction, it simply means you want to write them as separate fractions, like splitting them. So y goes for 1, you have a all over y plus b all over y negative 1. So when you multiply both sides by this denominator here, you have 1 equivalent to a into y negative 1 plus b into y. Now our aim is to find a and find b. There are different methods you could use here. You could either use the cover up method or use the other simple method, which I'm going to show you right now. Now the simple one is by setting, when you set y equals 0, and when you set y equals 0, this one here goes to 0, this man here goes to 0, so this one is left behind. You have 0 negative 1. So what you now have is going to be 1 equals 0 minus 1 is negative 1, so you have negative a. Now this implies that a equals negative 1. And then for the next one, if you set y equals 1, that is this y here, if you set y equals 1, this one goes to 0, so leaving this, so this is going to be b times 1, which is going to be b equals 1. So set y equals 1 will have b equals 1. So in continuation, so we obtain a to be equal to negative 1 and b to be equal to 1. So we're going to substitute these two values into this equation here. So you have 1 all over y into y minus 1 equals negative 1 all over y plus 1 all over y minus 1. And then we're expected to integrate both sides. So this is what we were meant to do before initially. So doing this is as good as doing it for this side and then doing it for this side. That is integrating both sides. You understand? So like what we now have is, when you integrate this, you have negative ln of y plus the ln of y minus 1. And then what we had was, in the right hand side was the integral of 1 over x dx. So this is going to give us negative ln of y, or let me write it as ln of y minus 1 minus ln of y. I just brought this to the other side, and then I brought this to the other side here. I laterally inverted that. So equals the ln of x plus c. Now when you do this using the laws of logarithm, this is the same thing as ln into y minus 1 all over y equals, now since this is an arbitrary constant, it is simpler when you rewrite it in terms of logarithm, probably as ln of b. Ln of b is also as good as an arbitrary constant, so it could represent the arbitrary constant here. The reason why I did this, or why I rewrote the arbitrary constant here as or in terms of logarithm, is to make an easy simplification. Even if you had written it like this, you will still get the same answer, or you still get a very good answer. But to make your work less rough, and probably to define an easier way of finding y, when you have the right hand side in terms of logarithm, then it makes more sense, or it makes the whole work simpler when you write the arbitrary constant as a logarithm. The reason is this. Now when you leave this, let me write this as, you have the ln of y minus 1 over y equals, now looking at this 2 now, I could easily apply the laws of logarithm here. Since they are adding, this is just going to be the same thing as the ln of bx, which wouldn't have been possible if it was ordinary c. So you see, that's what makes it very easy. Now to make this whole work simpler, let's do away with this, because if this equals this, so this implies that, to simplify the whole thing, let me just write this is going to be bx plus or minus bx, so which I'm going to call y minus 1 over y equals my plus minus b, let me call it cx. So our aim is now to make y the subject of the equation y. We're told to find an explicit solution of the differential equation. So it simply means the solution you're going to obtain should have y as the subject of the equation. So to make y the subject of this equation, let me make y let me cross multiply both sides by y. You have y minus 1 equals y times cx. When you bring this to this side, you have y minus y times cx equals 1. So y is common here. So you have y, when you make y the subject of formula, you have 1 over 1 minus cx. So this is the general solution for this differential equation. So the next thing we are going to do is to use the initial condition so we can find a particular solution for the initial value problem. So in continuation, we had this as the general solution of this differential equation. Now to implement the initial condition we were given, we are told that when x equals 0, y is 1. So when x equals 0, y is 1, you have 1 equals 1 over 1 minus x times 0. Oh, sorry, this should have been. So now the next thing is to implement the initial condition in the general solution we obtained. So trying to do that, we have when x is 0, y is 1. So you have y is 1 when x is 0, 0 times c. So our aim is to find a value of c. Now what you observe is, looking at this part here, no matter the value of c we put in here, as far as it's multiplied by 0, it still satisfies this initial condition here. So this implies that for all values, or let me just say all real values of x, let's leave this out, all real values of c satisfy the initial condition. Because anything you put here, any value of c you put here, it still gets multiplied by 0, and then it still satisfies the initial condition. So because of that, we have our general or our particular solution. You can call it general solution. Anyway, this is going to be 1 minus x into c. So where C is any real number